Hello friends, today we are going to deal with this topic called transport phenomena, and this why this transport phenomena is important. That is also worthwhile noting. This transport phenomena is a kind of physical uh, happening, a physical effect you can call it, which is responsible for transferring a physical quantity like mass, energy, or momentum from one point in the space to other point in the space. We wanted to see how effectively we can transfer these physical quantities, which are denoted by the letter h, from one point in the space to another point in the space effectively. That is the definition of transport phenomena, which is under the discussion. Suppose we are having a plane like this. In case of, for example, you consider the movement of a water in a pipe. That is a good example of a mass transferring from one point to another. So in that, you will find, first let us do this. You will find from this steady state condition, if this is considered, and if this is the velocity and this is the z-axis, and this is the flow of the water in a pipe. So effectively the mass is being transferred like this. So why can I call this as a steady flow? Because the gradient over here, dV by dz, is constant. That is the reason. This shows the reason why you can call this particular flow a steady flow. Why you can consider this particular motion as steady flow. For example, if our physical quantity under consideration is suppose h over here, then the effective quantity of h at this point P1 would be P1 equals to h minus dh by dz, z, and at P2 we will have h minus dh by dz into z. Here P2 is pointed here. So suppose if we can consider the transfer of mass, the difference in the transfer of mass that is happening between point 1 and point 2 has to be determined in order to understand the transport of this physical quantity that is happening in this particular system. Why this is important? This is important because If we had not known this, then we would not be able to know how the liquid behaves in that particular system. Suppose the behavior of liquid like water is different in some other system, in flow of liquid within this pipe is different as compared to some other viscous liquid like some chemical that is flowing, like petroleum is flowing into this pipe. So the viscosity, which is actually independent, which is dependent upon the mass of this mass of the uh, point which is under consideration. Actually, the viscosity is responsible for the amount of transport that can happen within this particular pipe per unit time is important. So that is the reason why we are doing this transport phenomenon. So now let us keep this particular thing in consideration while we deduce the further steps. Now, what happens in this case is that, suppose DNC is the number of molecules within the velocity range C and C plus dc, and and PC is the probability of collision, and obviously the number of molecules per unit volume. Volume is the definition, and we have del T is the time of interest. So we can write the number of molecules that are moving in the velocity range C and C plus dc with the collision probability of Pc in time dt is dnc Pc del T into del V. Obviously, del V is the volume that is taken under consideration in this case. So now, for this volume under consideration, suppose this is a volume under consideration, we consider a surface S, and our point is over here, and this point, from this point, the particle have all equal possible directions to move. So, the amount of particles moving towards this elementary surface dA can be given as dA cos theta by 4 pi r square dnc Pc del T. Now, you can use the spherical polar coordinates to represent this del V. So our dA by 4 pi, then we have dNc PC del T del V is R square sin theta cos theta d theta d phi d, and 4 pi r square was there, and we have r square over. So this is it. So r square cancels, and we can replace this as c by lambda. Then we have dA by 4 pi into dNc, it is c by lambda. Then we have del t sin theta cos theta d theta d phi. Now the next point we have from the survival equation, from survival equation we have the fraction of the number of molecules that travels the mean free path distance lambda without collision is e to the power minus r by lambda. This is the ratio that means it is n by n0 is equals to e to the power r by lambda. Suppose the particles put n number of particles out of n0, which is the initial condition, n0 particles, this ratio should be equals to r by lambda. This is the survival equation as so far we know. So multiplying this, we will obtain the number of particles that traveled the mean free path distance without collision will be this. Maybe this dA into 4 pi c dNc, then we have del t sin theta cos theta d theta d phi, then we have e to the power minus r by lambda dr. So this is the expression for the number of molecules that are passing through this area dA, subtending an angle, subtending a solid angle of d omega, and without collision is this. And now we shall impose the transport phenomena, main transport values to this equation to get the net transfer value that will be imposed on this system. So we'll write T at the top. Remember the point P1, we consider that it was at the top, so we can write T top equals to dA by 4 pi C dNc, then we write del T, then sin theta cos theta d theta d phi e to the power minus r by lambda dr. And for the up portion we have, you can consider for the point P1 dH by dz into z, and z will be replaced by r cos theta. So T up and so T down will be just the same thing written, but we'll have h plus dH by dz into r cos. This is the expression for the net transport of the physical quantity in the P2 direction. So the net flow will be F is equals to modulus T up minus T down is equals to 2 into dA by 4 pi C dNc del T into sin theta cos square theta d theta d phi e to the power minus r by lambda d. So this net equation can be found, the net transport that is happening in this whole system can be found by integrating this whole system within the limits. The value of C ranges from 0 to infinity, and theta is equals to 0 to pi by 2, and phi equals to 0 to 2 pi, and r is also running from 0 to infinity. So F can be written as F is equals to dA by 2 pi, this remains 0 to infinity C dNc, and here you can put del T also over here. So, and 0 to pi by 2 sin theta cos square theta d theta turns up to 1 by 3, and 0 to 2 pi, this is 2 pi, and this turns up to, and there is also one term that I have missed over here. You can write it over there as one r should be written into r, another value dH by this was forgotten, so I have to write this. So C dNc 1/3 2 pi, and this integration would lead to lambda into gamma 2 into dH by dz. So we have this 2 pi gone, so you can write it over here. Like this. F by dA dt, or let it look like this, like this, 1 third dt dth by c lambda, and for this you will write as c dnc. Leave it like this, c dnc. So this is the expression for the transport of the physical quantity from one point to another for that considered amount of time interval with a considered amount of surface area that is there in the system. So that's all. Thank you very much.